Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to this channel Chandan Physics. In this video, we are going to discuss uncertainty principle. Let's begin. The uncertainty principle is defined by the scientist W. Heisenberg. According to his name, this one is called as Heisenberg's uncertainty principle. What is that of principle? The uncertainty principle states that it is impossible to measure simultaneously two canonical conjugate variables. It's impossible to measure simultaneously two canonical conjugate variables. Now we define what are the canonical conjugates variable and what should be the mathematical approach to that particular principle. If Q and P are two canonical conjugate variables, then their product, the product of the uncertainty in Q and uncertainty in P is greater than equal to h cross by 2, that is h cross means h by 2 pi, that means del q into del p is greater than equal to h cross by 2. Del q, that is the uncertainty in Q, del p, that is the uncertainty in P. The product of uncertainty in Q and uncertainty in P is greater than equal to that particular quantity h cross by 2, where h cross, that is the h by 2 pi, and h is known as the Planck's constant. Now, what are some physical quantities which are under the category of canonical conjugate variables? How we define that particular term, canonical conjugate variable? There are so many canonical conjugate variables like position, momentum, energy, time, and azimuthal quantum number, and angular momentum, orbital angular momentum. These are some canonical conjugate variables. That means we can't simultaneously measure both of these physical quantities at a particular time. It is impossible to measure simultaneously that two canonical conjugate variables. Now, first, if del x here in that of case del q, that is uncertainty in position, let me assume that is uncertainty, not position, that is uncertainty in Q, uncertainty in Q, and del P here, that is uncertainty in P. Now we define the canonical conjugate variables. Let del X is the uncertainty in the position coordinate x, and del Px is the uncertainty in the x component of momentum. Then the product of uncertainty in position and uncertainty in momentum in that of x coordinate is greater than equal to the quantity h cross by 2. Let me prepare equation number 1. Similarly, for y axis it will be del y del Py greater than equal to h cross by 2, and for z axis it will be like del z del Pz greater than equal to h cross by 2. Equation number 3. These three relations are basically named as the position momentum uncertainty relation. Position momentum uncertainty relation. That means position and momentum, these two are the canonical conjugate variable. Again, the other uncertainty relations relations are like this, that is del phi del Lz greater than equal to h cross by 2, that equation number 4, and del T del E greater than equal to h cross by 2, that is equation number 5th. Look at here these two equations. One is where phi is the azimuthal angle. Here we write like this: phi refer as azimuthal angle, and Lz be the z component of orbital angular momentum. And that is uncertainty relation in azimuthal angle and orbital angular momentum. Here that equation is the uncertainty in, that is time and energy. Time, energy, uncertainty relation. Uncertainty relation. That one is the uncertainty in azimuthal angle and orbital angular momentum. Here is the uncertainty relation, that is time energy uncertainty relation. Look here, what should be the physical meaning of these uncertainty equations? From that of equation 1, if one measures the x coordinate of the particle with 100% accuracy, that is del x will be 0, that is uncertainty in position will be 0, then del px tends to infinity. Otherwise we can say, if x component of linear momentum, x component with linear momentum, that is del px with 100% accuracy, that means del px will be 0, uncertainty in momentum will be 0, that leads del x tends to infinity. Let I define what that particular equation indicates. Equation 1, from equation 1 we conclude, from equation 1 we conclude, if someone measure, if one measures that x coordinate of the particle with 100% accuracy, that is del x will be 0. Here at that case del px tends to infinity. Similarly, or we can say it as otherwise if x component of linear momentum, x component of linear momentum with 100% accuracy, that means del px is equal to 0, that is uncertainty in momentum del px is equal to 0, then that leads to del x tends to infinity. This is the physical meaning of this type of uncertainty relations. From these above discussions we conclude that both the above variables cannot be measured simultaneously with 100% accuracy. What are the conclusion? Here you can write, the canonical variables cannot be measured simultaneously with 100% accuracy, as that particular principle indicates. Okay, the canonical variables cannot be measured simultaneously with 100% accuracy. This is all about the uncertainty relation or the uncertainty principle that was proposed by W. Heisenberg, sir. This one is the statement, and we mathematically write that statement and some examples of that of uncertainty relations and its physical significance towards uncertainty relation, and finally the conclusion of that of uncertainty relation. So, with this useful and informative notes, let me wind up this session. Thank you.